If I look at 16 and 32, 2 goes into both those. So we could say 16 divided by 2 equals, actually, let's do by 2 works. Equals 8. 34 divided by 2 equals 17. So this looks like an 8, 15, 17 primitive. Well, to get 16, 8 times 2 equals 16, 17 times 2 equals 34, so 15 times 2 equals x equals 30. So the big question today was, in the other class, was on some of them they used Pythagorean triples, other ones they didn't recognize them, so I just used a squared plus b squared equals c squared. That is fine. I wanted you to try your best on these primitives, because like this problem is super easy if you recognize the 8, 15, 17. It takes almost no work at all. You can just go, okay, oh, that's 8, 17, just multiply by 2. Okay, that's 30. Versus someone else doing a squared plus b squared equals 34 squared, typing that in your calculator, doing your subtraction, doing your square root, and hopefully you get out the right answer. Okay, so Pythagorean triples just save you some time. That's the long and short of it. But if you don't use them and you just use a squared plus b squared equals c squared, hey, as long as you got time to finish everything, you are fine. That being said, I know we have questions on these. I'm going to do one more with you guys, but I would like you to try that last one. All right, we did number 19 together. Now let's do number 20. So 20 is going to follow almost the exact same idea. Remember, this circle has a radius of 1 unit. So that means this length on number 20 is 1. That is the length of this line. Well, just like this one, I dropped a 90-degree angle down here. I'm going to do the same thing here. I'm going to drop a 90-degree angle that's going to be perpendicular to the x-axis. This really is our x and y axis. If we look at this 150, to go all the way around, it's 180 degrees. So this is 150 of 180. So that little sliver right there is 30. That's pretty tiny. Is 30 degrees. Which makes this one 60 degrees. So I'm just going to redraw that triangle down here so I have a little bit more room. We now have a 30, 60, 90 triangle with a hypotenuse of 1. Well, with a 30, 60, 90 triangle, we label this, the side across from 30 is our S. The one across, bless you, from 60 degrees is going to be our S square root of 3. And the one across from the 1 is, or 90 degrees, which is our 1, is going to be 2S. So 2S is pointing to 1, so that means 2S equals 1. So divide both sides by 2, you find out that S equals 1/2. So this length right here is 1/2. The S square root of 3, plugging that 1/2 in place of that S will be 1/2 times square root of 3, which would probably be easier to put as square root of 3 over 2. Well, that means this length here is square root of 3 over 2. Here's the slight difference between what we get here and what we're going to put here. This is the xy plane. We said yesterday to go in this direction, we have to have a negative x value. So on the xy plane, I'm going to label this as negative square root of 3 over 2. And I'm going to label this as 1/2. I only do that so I can get this point. This point right here would have the x value negative square root of 3 over 2 and up 1/2. So that is that point on the xy plane. Yeah, Labib.
Are the hypotenuses always 1?
Yes, it's a unit circle, so so we know that for a fact because this is the point 1, 0, this is the point 0, 1. So this is a circle with radius 1, so any radius is 1, and each of these are just a radius. All right, other questions from the homework? Labib. you have a specific question?
Yeah. So is the main structure, is that not a rectangle?
It is not necessarily a rectangle. And in fact, Jacob, I was wrong with what I said to you yesterday. Because you said, do we know in number 17? Did I not put that? Oh, I do have it there. In number 17, I told you that these would be right angles as well, because I thought we knew these. I was looking at a different problem.
Yeah.
I thought both those were the same length. If they were both the same length, then it would be. These aren't necessarily 90 degrees.
Yeah.
And in fact, we don't need to know those measures. We just need to know this 30 degrees here, because we can then say that this is 60 degrees. With a 30, 60, 90 triangle, we can then find V, and we can then find W. Well, once we find W, I have a right triangle, and W ends up being, I think, 20. So let's just pretend like this is gone for a second, and we actually have, we actually have 20 in its place. Now I have a right triangle with 16, 20, and missing this side, which is Pythagorean triple, because you divide by 4, and this would be a 4, this would be a 5, so this would be a 3 times 4, so this would be 12. And then we'd have another Pythagorean triple here. So it actually goes pretty quick once you recognize that 30, 60, 90. You do have to do that work, but after that, the rest were Pythagorean triples. Kind of the same thing on number 18. Number 18, we have a right angle there, which made this one a right angle, which made this one a right angle. And then, because both of these are the same, this is a 45 degree, this is a 45 degree angle, and this is 120, 130, so this is going to be a 12, 13. We can figure out A from our Pythagorean thing, which make A the exact same thing as here, which we could find B, which would help us find D and C, if anyone has questions on that one. All right, other questions from the homework? Okay, then let's go over to today's lesson. Today's lesson is going to be a little bit of a drag starting off, but we're going to find a much easier way to do it. We're going to talk about the geometric mean first. The geometric mean is a concept that you should at least have seen. It's not a concept that's going to be, it's not going to be in the homework. All right, it's not a huge concept. But the geometric mean, which starts right there, is when the means of a proportion are basically equal. I forgot how exactly I worded it. I want to word it the same way in both classes. So I just put are the same. Are equal or are the same. So the geometric mean is when the means of the proportion are the same, and that number is going to be called the geometric mean of the extremes. The two other numbers are not going to be the same. So a geometric mean is going to look something like this. Number 1 says, find the geometric mean between 8 and 10. So 8 and 10 are going to be your extremes, and your geometric mean is going to be that number that can replace both of these x's. So what is that number where this mean is the exact same value? So when I ask for a geometric mean, you just set it up as a means extremes, putting your two extremes as 8 and 10, and making sure these are the same variable. So in this case, you would do your means extremes, which you'd multiply 8 times 10 and x times x, so you'd end up with x squared equals 80. You take the square root of both sides, and you'll have x equals the square root of 80. What perfect square goes into 80, though? Labib? 4. Does anything bigger go into it? 4 would work. You just have to do it again. Yeah. 16 actually goes into it. 16 is the easiest, but if you were on the test and you just did 4, you'd reduce and go, okay, 4 goes into it again. I got to do it one more time. So we have square root of 16 times square root of 5, which equals 4 square root of 5. So basically, that 4 square root of 5 links these two together. That's what the geometric mean says. To find the geometric mean between 9 and 12, we just set it up with 9 and 12 being our extremes, and we make sure our means are going to be the exact same value, so I put the exact same variable there. Then we do our cross multiplication to give me x squared equals, that'd be 108. Then we take the square root of both sides, and we have x equals the square root of 108. But that isn't simplified. 9 actually goes into it, and 9 goes into it 12 times. Times, oh, hang on. What's something bigger that goes into 108? I don't know why I did 12. I mean, there's a bigger one. Well, 36 goes into it. 36 would be a much better one. It would be a little bit quicker. How many times does 36 go into it? 3 times. That's going to equal 6 square root of 3. Once again, it's kind of a small blurb. I'm not expecting it on the homework. It's good that you've seen it, because it's kind of what what we're going to be talking about today is based upon, but I'm generally not going to ask you to do that. All right, let's take a step back. Let's go on our way, way back machine. Our way, way back machine, when I said that we had similar triangles that had a ratio between each similar triangle. Remember, each similar triangle has a ratio between the two. Well, we're going to look at a very specific triangle. We are going to only look at today right triangles that have an altitude. Once again, and I'm going to say it a billion times, that's all we're talking about today is a right triangle with an altitude, which looks like this. If you take a right triangle and you draw an altitude, you have now created 3 similar triangles. You don't need to prove it. It's just 100% fact. And those 3 triangles are this one, and the big one. When we draw similar triangles, I always tell you draw them the exact same way so you know what stuff relates to what or what corresponds to what. So in this example up here, I would draw all of my right triangles to look like this. Because as I have these drawn, now I know what triangles are similar to which triangle. So that's all we're going to name on that left-hand side. Basically saying that triangle ACB is similar to triangle, and we can do the exact same order, ADC. That's why we write them all the same, so I can easily write down what's similar in the triangle, and I can put the parts down secondly. All right, then we also know that triangle ACB is similar to triangle CDB. CDEDBDB? Is that around anymore? No? Yeah. I don't know, when we were kids, we were always like CDEDBDB, because it's just letters, but they're also words. Get it? CDEDBDB. CDEDBDB? No, anyway. All right, and we also know that triangle ADC is similar to triangle CDB. All right, then we can come up with some ratios. We're going to do it on the next one, but our ratios would basically be, you could do A over C, or AC over AD would be the exact same thing as CD over DC. Or you could do A to B over C to B would be the same thing as CB over DB. We did that to find a missing segment, and that's what we're going to do in this next problem. So example 3. Example 3 says, identify the similar triangles, then find the value of x. So what I'm going to do is I'm going to draw, I know there's 3 similar triangles. So what I'm going to do is I'm going to draw 3 triangles that look the exact same but are in descending order of size. So something like this. And then that's a little bit smaller. Not terribly important. We draw it perfectly to scale. Then we're going to label them. Well, the big one is that EGF. And we have some numbers we can put on there. E to F is 5. E to G is 3. And finally, G to F is 4. All right, the next triangle I'm going to draw is the ones that are consistent of that H, that G, and that F. Can we all picture that triangle? Well, if I'm looking at, maybe I'll highlight it too. So we're highlighting this triangle here. That's what I'm looking at. Well, our H is right by that 90 degrees. So that means on the 90 degree, we're going to put the H there. H to F is longer than H to G, so F is going to be the bottom right, and G is going to go on top. Then we look back at our drawing. H to G was actually X in length. Our H to F, we don't know that length. G to F is that 4. Our last triangle, H is once again the 90-degree part of it. Then we'll have G and E. E to G is 3. H to G is X. Now, each of these triangles are similar, and the corresponding parts are in the proper places. So if I needed to find X, I would say, well, look at that 5/4. That links those two triangles. That is our corresponding ratio, the ratio between the two triangles. So I'm actually just looking at EGF and GHF. So I'm looking at that 5 and that 4. Those are corresponding parts, so we'd have a ratio of 5/4. Well, then I can look at that 3 and that X. Maybe I'll even do a different shape. I'll do the 3 as a square. That X is a square too. So 5 was from the big triangle, 4 was from the smaller triangle, so this is just going to equal 3 comes from the bigger triangle and X comes from the smaller triangle. Now I can just do cross multiplication, which will get me 5x equals 12, and we'll just have x equals 12/5, and that's as far as we're going to go on that one. I'm not going to reduce it to a decimal. This is the hardest way to find missing segments of an altitude of a right triangle. Remember, the only thing we're covering today is altitudes of right triangles. That's the only thing this is going to apply to. We are going to look at an easier way to do that, which is just going to be drawing pictures to find those exact same ratios. And we have two different methods to do that. We have one called the heartbeat method, and we have one called the bunny ear method. The heartbeat method matches. The bunny ear method, you're going to have to stretch your imagination a little bit to see the bunny ears. Yeah, you'll see in just a second. All right, heartbeat method. Heartbeat method is a 4-step process. Our first step is we are going to draw a line from A to D. And I'm going to kind of make a thicker line so we can see it. So I'm going basically over here. I just drew a red line from A to D. Here's where the heartbeat comes in. We are now going to go from D to C. So we're going to go up that line, and then we're going to fall down again. We're going to go from C back to D, which is going to look something like that. And then finally, we're going to go from D to B. Does that look like a heartbeat? Kind of. You know, when you're doing the boop, boop, boop. That's why I call it the heartbeat method. But what did that do? I just drew a picture on there. That picture actually shows you a whole ratio compared to another ratio. Let's go back. I went from A to D. So what you're going to do is you're going to start by writing AD. Then I ran from D to C. Well, I'm just going to name that line CD. You can call it DC or CD. It doesn't matter. But then it's going to equal to, we go back down CD. So we're still at CD. And then we go across to DB. Now, if any of those parts are missing, you can solve it. And that's what we're going to do down below. So that is AD over CD equals CD over DB. Note, CD and CD are the exact same value. These two will always be the exact same value. We are using that geometric mean we kind of talked about just before. Yeah. We have another method called the bunny ear method. This method helps if I'm looking for any of these values along these particular 4 spots, right? The bunny ear is going to help us get different ones. So bunny ears is going to go from A to B. So you're going to run around that whole length. And if you want it to look like a bunny ear, you got to kind of accentuate it. So we have A to B. So following that pattern we did before, we're going to write AB down below. Now we're going to run up that CB line. So we're going to go from B to C. Well, that's that segment CB. Knowing that we're using geometric means, we have to go back down CB. So we're going to go back down CB. And unfortunately, we can't go back to A. We're going to go back to D. So it kind of ends that nice bunny ears that we could have, but it's almost bunny ears, right? We got one bunny here, we got part of one here. That's why I said you got to kind of stretch your imagination. That is part of your two bunny ears. So that is AB over CB equals CB over BD. Once again, the CBs are both the same because we're using that geometric mean. Those both numbers have to be the exact same. So depending on what I'm looking for, I should probably finish writing here. So we went from C back to B, and then we went from B to D. So depending on what information is missing or what I need to find, depends on what method we're going to use. Do we all have the bunny ear method at least written down and the order and stuff?
Yeah.
Okay. If you need me to go back, let me know. All right, our first example, we're going to do 4 and 6, and then we'll do 5 and 7. 4 and 6 are both going to use the heartbeat method. Because if I draw my heartbeat on number 4, we'd go across here, we'd go up, we'd go down, and we'd go across that Y. In that same order, you went across 12 first, then you went up 18, you came back down 18, and then you ended with Y. Now, like Davion, a good thing to pay attention to is the fact that you can go both directions. So you could do Y over 18, 18 over 12. It doesn't matter. I usually go left to right because that's how I read. That's how I do math. So typically I go left to right, but it doesn't matter. All right, now we use cross multiplication. And we are going to have 12y. Let's make sure my numbers are correct. Equals 324. 324 divided by 12. I got y equals 27, unless my math on there is incorrect. Cool. Next one, heartbeat method as well. If you draw the heartbeat method on the next one, it's going to cover all our bases because we go from 5 over y equals y over 8. So once again, we'll have 5 over y equals y over 8. If these two are ever not the same, you did something wrong. We're using geometric means to solve this, so these two have to be the same. All right, so we're going to have y squared equals 5 times 8, which is 40. Then we're going to have y equals the square root of 40. Well, 4 goes into 40 10 times, so we'd have the square root of 4 times the square root of 10, which would just equal to square root of 10. So y equals 2 square root of 10. Any questions on the heartbeat method? All right, for 5 and 7, the heartbeat method isn't going to help us. So if you look at number 5, if I do the heartbeat method, I'll have this over this, over this, over 16. So I'd have, I guess we could write this as z minus 16. We could have z minus 16 over something equals something over 16. It's not going to be enough to solve. So our heartbeat method isn't going to work on this one. Instead, we have to use the bunny ears. With the bunny ears, you got to make sure you run up the right number. For instance, if I go this direction, I don't get a lot of information. However, if I go the opposite direction, so if I go across here, that's z. If I run up to 27, that's 27. I go back down 27, and I go across that 16. So in this case, following my writing, I would have z over, so I went across z, I went up 27, so it'd be over 27, equals, I go back down 27, and I go over 16. In this case, I'm going to have 16z equals 729. In this one, I'm just going to round to the nearest tenth. I didn't give any specific direction, so this one I'm just going to round to the nearest tenth, and I got 45.6. Look at number 7. Oh, did I come up with something different?
Oh, I just have a question.
Yeah.
So how do you know when you use heartbeat or bunny?
A good method to know is if the altitude's ever labeled, you're probably going to use the heartbeat. If we have one of these sides numbered, then you're probably going to use the bunny ears. All right. And draw a picture. Draw it. And if you're not getting enough information, try drawing another method. Go a different direction, go up another number. Sometimes it won't stand out. Like these are pretty clear cut which ones you should do, but sometimes in the homework you'll have X's and Y's buried in there and you just kind of have to try something and see if it works. If it doesn't, try a different method. Yeah, absolutely. You can use my colored pencils. Yep. All right, for number 7, I want you to move that X. That X isn't in the right place. I don't know how that X got moved. I wanted it over here. That way, when we do our bunny ear method, we're going to go across 8. So I'll have 8 over X is going to equal, well, it has to be X because we're using geometric mean, but in the drawing it supports it. We'll have X over 2. Well, X times X is X squared equals 16. Take the square root of both sides, loop, loop. And you should just have X equals 4. That is the sound of taking a square root of both sides. If you didn't know that, I don't know what world you live in. You should at least do that in your head. All right. Yes, John.
Can you show me that order again?
Yeah. So we're going to go across 8. So that's where I got the 8 from. Then we go up X. That's where we got the X from. Then we come back down X. That's where the X comes from. And then we go across the 2.
Okay.
You kind of know you did it right because these two better be the same and these two better be different. If you ever have 8 and 8, it meant you went too far and you did something wrong. So these two should be different. These two should be the same. All right, just 2 more. Number 8, we actually have to use 2 different methods. So Labib, this is kind of one of those times where you draw a picture and see if it works or not. So don't draw this picture. This is actually going to be the wrong first step. But maybe I'm looking at this, all right? I'm putting my bunny ears on. And what that would be, and I'm going to erase this, would be 16 plus X over Y equals Y over X. Does that look like you're going to be able to solve much of it? No. And you could start it and figure out, well, I got 2 variables. I'm not going to be able to solve it. So maybe then you go back to the drawing board and you're like, well, let's try heartbeat. Heartbeat would give me 16 over 12 equals, we go back down 12 over X. That looks a lot more manageable, doesn't it?
But you don't know what the value is.
Well, let's do this first. Let's find X first, and then we'll see if that gets us anywhere else. So if I do the heartbeat method, at least I can solve one of the variables. Maybe I can't find Y. Maybe on the test, I don't get Y, but at least I get one of the variables and I don't quit. All right, so we're going to have 16X equals 144. Divide 16 on both sides, and at least I have X equals 9. At the very least, I solve for one of them, I get those points. That being said, if I look at X as being 9 instead of X, that opens the door to the heartbeat method. I'm going to draw the heartbeat method in green. The heartbeat method is going to go all the way across this long thing. Instead of writing 16 plus X, now I can write 25. All right, so now I have 25. And I go up that Y. I still don't know what Y is, so we have 25 over Y. We come back down y, and we go across that 9. And now this is something we can solve. Now we can solve for y, because I can go y times y is y squared. Is going to equal 9 times 25, which is 225. And we take the square root of both sides, and you should come up with y equals 15. So you may have to find your first variable and use that to find your second variable. So if ever your picture doesn't look like you can solve something, then go ahead and use this method. Yeah?
How do you know where to start from? So why can't I, no, wait, never mind.
You sure?
Yeah.
Okay. Are you saying like where do you start your bunny ears?
No, I was gonna ask where do you start your heartbeat, but then it has to go across the altitude. So.
Yes, it has to go across. So you can't go down here, right? It has to be across. Yep. Your altitude is going to be your heartbeat. That's how you know where to go. All right, you guys are responsible for that last one. I'll give you the answer to it. I got b equals 3 over 2. As soon as you get checked off on that, the rest of the time is yours. Actually, just either you got it or you don't got that last one. The rest of the time.